Everyone knows and loves RPCs. Today, I will talk about how RPCs are insufficient for smart spaces, and in this work, we propose an alternative. Smart spaces support automations, also known as routines, which are usually sequences of actions that are triggered by humans, time, or sensor events, and supported by Alexa, Google Home, and other assistants. Now, imagine a simple routine where users would expect it to work. The garage door opens, and the trash can moves outside. Such smart trash cans are already on the market. Then the garage door closes, and the trash can is ready for pickup when the trash truck comes. But now think about a scenario where the trash can gets stuck below the garage door on its way out. And that can be because of an obstacle or a jam. Closing the garage door at this point creates a safety violation because the garage door cannot fully close when the trash can remains stuck below it. Preventing this requires knowing what stage each action is in, not just whether a command was acknowledged by the smart device. The stage is unknown because actions in smart spaces are not instantaneous. Opening a door takes seconds. Elevators and shades take tens of seconds. Heating a room takes minutes to hours even. These actions are physical, slow, and unpredictable. But despite this, today we expose them using one-shot remote procedure calls, or RPCs. Let's try to fit RPCs into the IoT world. There are three variants that are possible. We're going to use as an example the action of a smart vacuum cleaning the living room. Initially, a request is sent to the remote device, which can be initiated by an automation or by a human. Traditionally, the reply is sent back when the request is received, as an acknowledgement before anything actually happens. In this case, this corresponds to the vacuum receiving the request. Let's call this RPC ACK. And there are more options to consider here, though. A second option is to place the response when the action starts, or after any preconditions for the action start are checked as satisfied. In this example, start means the vacuum reaches the start location after moving from the docking station in the hallway to the living room entrance. Of course, an obstacle might actually prevent this from happening. Let's call this RPC start. Lastly, the reply can be sent back when the action execution has been completed by the IoT device. In the vacuum scenario, this means that the device is on its way back to the docking station. The action may not complete, though, if the vacuum runs out of charge before finishing its lengthy cleaning cycle. Let's call this RPC complete. Now, since a physical action can fail at any of these stages, we argue that a single-shot RPC cannot actually sufficiently express an action's execution. Basically, all these three RPC options leave us between a rock and a hard place. We need an overarching abstraction to make failure observable to users and to routines. We handle both in this paper. We introduce a new abstraction on top of RPC called RASC, or Request Acknowledgement Start Complete. RASC moves us away from the single-point reply of traditional RPCs and instead provides upper layers a structured way to observe these critical points of a physical action. First, the client sends the request to trigger the physical action. The device, or its cloud app, immediately returns an acknowledgement which is delivered to the client. Then the runtime returns a start notification and a completion notification. In the background, these state changes are detected using a limited budget of RPCs. Now, imagine we want to have the vacuum clean the living room, but it needs light to navigate. And our objective is to build an energy-saving routine around this goal. If we rely on the RPC ACK paradigm, we can turn on the corridor light as the vacuum leaves the docking station in the hallway upon acknowledgement, which makes a routine of sequential actions. Now, when the vacuum reaches its start position at the living room entrance, we need another routine to turn on the living room light and turn off the hallway light. And then, when the cleaning is over, we need yet another one to turn off the living room light. At this point, what should be a single intuitive routine has turned into 3 separate routines, each relying on timing assumptions or coarse triggers, which might overlap among some routines even. The problem is similar if we rely on RPC start or RPC complete. However, our abstraction RASC's observability points enable more expressive programmability in smart spaces. In this example, we can create one single routine that takes advantage of the new hooks we observe. Once we make actions observable and programmable, challenges and design goals arise. One is mutual exclusion. That is, no device may execute more than one action at a time. Further, routines or automations act like transactions over shared devices. So even if multiple routines execute concurrently, the outcome must be equivalent to some serial order. And finally, there is polling efficiency. To observe action progress and failures, especially for poll-only devices, we need to detect state changes quickly without overwhelming devices or vendor APIs. So we can now support diverse programming hooks and workflows. In particular, we support co-actions upon action acknowledgement and start, extending the commonly accepted model of a sequence of actions, and fallback actions upon action failure. Our system RASC internally expresses routines as directed acyclic graphs with a dependency type on each edge. So RASC is our abstraction, and RASC is our system that implements it. I may use the 2 terms interchangeably during the talk. RASC's 3 points of feedback, act, start, and complete, now allow us to push up planned actions so that they can start earlier or later while still obeying dependencies. We adapt existing smart space scheduling algorithms to support scheduling routines with fine-grained dependencies when they are triggered. And when there are real-time action length deviations, we identify the set of affected actions on the schedule and also an immutable serialization order that is enforced by the already running routines. We reschedule them with algorithms based on shortest task first and related work called restriction vectors from real-time systems literature, which obeys dependencies across tasks. And we do all this while maintaining mutual exclusion and serial equivalence guarantees. You can read our paper for more details on the scheduling and rescheduling policies. Remember that RASC is layered atop RPCs. How do we achieve this? A key constraint we run into in practice is that a large fraction of device vendors only expose poll-based APIs. That means the system has no way to get pushed updates about when an action actually starts or finishes. A natural first idea is periodic polling. But that quickly runs into a trade-off. If we poll too frequently, we overload devices and vendor clouds. And if we poll too slowly, we detect failures or completions far too late. So the challenge is how to place a small number of polls intelligently so that we detect progress quickly without overwhelming the system. In particular, we formulate the RPC placement problem as such. Given an expected upper bound U for the action stage length and a budget for how many poles we can place, the goal is to minimize the state change detection time. In this case, if an action completes after pole L3, Q depicts the detection time. We identify that there is an opportunity to use historical data to efficiently place these poles. Our system RASC models the detection time Q with this formula. Here, each pole can detect all start or completion times before that and after the previous pole, with a certain probability. Similarly, other poles will detect completion times in their respective intervals. Intuitively, the expected detection time is the weighted average distance from when the action finishes a stage until we next pole, over all possible completion times. Minimizing Q, we get the placement of the poles. Our adaptive polling works up to an estimated upper bound U, but real actions can exceed it because of interruptions by humans or environmental factors. Beyond U, RASC adapts based on what it observes. If there is partial progress, we estimate the remaining time and schedule the next pole without exceeding the detection time tolerance QW. For example, we initially expect the trash can to cover a certain distance and a specific amount of time based on the historical data. Once this action exceeds its expected duration, we look at how much progress we've seen so far and how fast that progress happened, and simply extrapolate to estimate the new total action length. In case there is no progress between poles, we use bounded exponential backoff up to QW to avoid overloading devices while still guaranteeing timely detection. We implemented RASC by extending the open source project Home Assistant. For adaptive polling, we evaluate with real action length data. We manually measure the actions durations for doors, shades, and elevators in our office building, and we use an existing data set for thermostat actions. To evaluate scheduling, we adapted routine traces from IoT Bench and SmartThings, and generated 2 arrival workloads, one with random intervals and one with random plus bursty arrivals, to capture both background and peak activity. Moving on to the results, RASC provides observability faster or comparably to periodic polling, while having low overhead in used poles. In this figure, lower and left is better. Similarly, CPU and memory overheads of the adaptive polling technique are low on the host machine when compared to periodic polling or no polling. The system is not efficient from the beginning. RASC initially polls periodically until it gets a few samples per action and only then starts applying adaptive polling. This figure shows convergence speed across devices. We need only 10 to 20 samples to stabilize the action length distribution. Short actions like doors or shades converge in about 10 runs, while longer actions like thermostats take closer to 20. The bottom figure looks at data drift as devices may change behavior over time. Using the Wasserstein distance, also known as earth mover distance, we see that RASC reconverges quickly, even when distributions shift. Moderate shifts, such as door versus elevator, with Wasserstein distance around 14, reconverge in about 20 samples. And much larger shifts still stabilize within roughly 40. If you hold an elevator door open, would RASC still work? In this case, a thermostat is interrupted. We plot false positives where an interruption is mistaken as a failure. False positives rise for long interruptions near the end of an action's end. But overall, RASC reliably distinguishes true failures from temporary interruptions. And here, red regions show extra poles beyond the estimated upper bound U. When an interruption is early or brief, RASC's overhead stays low. When interruptions last longer, polling increases. But the detection time remains low, which is what users care about. Finally, we look at the end-to-end impact of our dynamic scheduling algorithms. And across all experiments, RASC's variance outperforms strong baselines. In particular, it finishes routines 11% faster than the fastest baseline, reduces wait times by 33% on average and 50% at the 95th percentile, and cuts device idle time by up to 27%. While RASC sometimes increases end-to-end latency slightly, that overhead is modest, and it enables higher parallelism, about 10% more than the best baseline. To conclude, RASC is a new abstraction on top of RPC. Our system RASC extends the open source Home Assistant project and proposes adaptive polling and rescheduling strategies for cyber-physical actions. In summary, when we consider human-facing settings like RASC does, many exciting opportunities arise for the systems and networking communities. I hope this work encourages you to think about how bringing humans into the loop in your research may change your approaches or metrics. Thank you for your attention, and I'm happy to take any questions.